Right soon. Okay, so we are already 4 minutes late. Let's begin. Hello, everyone. Welcome back for the second half of day two. And it's my pleasure to introduce Vineeth. So Vineeth Balasubramanian is a principal researcher at Microsoft Research India and a professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Hyderabad, IITH, India. He's the founding head of the Department of Artificial Intelligence at IITH, and his research interest includes deep learning, computer vision, with a focus on explainability, multimodal learning, reasoning, and continued learning. So I think today Vineeth is going to talk about what can you do beyond catastrophic forgetting. So thank you.
So point is. Okay, thank you, Sharath, for having me here in the first place, and then also for the kind introduction. Happy to be here, and let me get started with the talk. Yeah, the focus of this talk is going to be beyond catastrophic forgetting. What does it mean to take continual learning to the wild? Let me start with a quick TLDR. So in case you choose to doze off after lunch, you probably can get a sense of what I'm talking about. Uh, Obviously, the focus of continual learning has been on mitigation of catastrophic forgetting. That's been the primary objective. Is that still the right direction for efforts in continual learning? Maybe a question that I'd like to pose. And I also want to just add that continual learning has a multiplier effect when you actually use it on top of real world tasks. So what does this mean and entail is perhaps the second aspect that I want to touch upon. And I do want to mention here that a disclaimer that this talk is not about LLMs, right? So, so yeah, there is a world beyond LLMs. Yeah, there is an AI/ML world beyond LLMs, and I still think continual learning is even more useful when you talk about models that are smaller, deployed on edge devices, and so on and so forth. Okay, let me get started. Okay, as everyone in the room knows, catastrophic forgetting has been the key challenge of continual learning for decades together. Started with the very famous McCloskey and Cohen study in 1989, where they showed that if you compare how humans remember and how neural networks remember, there was a catastrophic difference between how the neural network remembered things over time. Right, so well-known study. And over the years today, we also have survey papers that talk about defying forgetting to be the main goal of continual learning, or this particular snippet from this paper that says that the major challenge is to learn without catastrophic forgetting. Performance on a previously learned task or domain should not significantly degrade over time as new tasks or domains are added. Right? So I'm sure it's 101 for everybody in the room here. And to add to this, if you looked at I picked up a few survey papers in the last few years and did a quick keyword frequency statistics. And you can see here that forgetting continues to have the highest presence. The next few words were catastrophic, memory, okay? And then there's adaptation, reasoning, and privacy shows up a bit more. Right? So these are largely the keyword cloud of major survey papers in continual learning, in case you did not believe what I said so far, right? Okay, so now why am I saying all this? Let me move on to that. Let's now for a moment just try to imagine how humans learn and then come back to continual learning the way we all do it in AI so far. If you look at the memory itself, the human memory, right, you can view memory as an entity or as a function. Right? There are both views to it, if one could see. So I'm not a neuroscientist, but this is my understanding. If any of you is a neuroscientist here, please feel free to correct me on this. So when you see memory as an entity, there are multiple operative stages that you have on the memory itself. You have encoding, then there's a phase of consolidation, there's a phase of storage, and of course, there's a phase of retrieval. Right? So especially if you look at encoding, it's typically affected by how much you attend to the information, right? So that's how much you store. It can be influenced by factors such as emotion. When you feel very good about something, maybe you remember it. When you feel very bad about something, maybe you remember it. In between lukewarm, you're probably not going to remember it, right? So emotion does affect how you store your memory, or even how deeply you process something. influences what you store in your memory. And if you look at retrieval itself, retrieval is inherently a reconstructive process, and memory can be altered, updated, even forgotten during retrieval. I'll come to it in a moment as to give more details on that. Now, if I had to see the other side, right? So memory as a function, memory is largely part of a dynamic cognitive environment, that system for adapting to the environment. It's deeply integrated with perception, reasoning, and action. It generally works in tandem with other aspects of human perception and learning, which is attention, emotion, and general learning itself. And it also has other functions, right? So it can support simulation of future events, goal-directed planning, so on and so forth, right? So memory is far more versatile than just one dump of samples, right? So that's the point that I'm trying to convey. Now, what about forgetting itself, right? From human memory perspective, there are many well-understood causes for forgetting. Few of those that I could glean to put here is one of them, according to theories in memory and forgetting, is trace decay, which means the data does not appear as much as before. And as the data starts weaning, your memory also about that item starts weaning and you start forgetting. Then there's the interference theory, proactive and retroactive. This is very similar to forward, backward transfer in continual learning, where something that you learn new affects what you've learned in the past, or something that you had in the past affects what you want to learn newly, right? So there's interference theory. And there's also retrieval failure. How good your retrieval cues are, whether they are absent or inappropriate, may define what you retrieve from memory too. Right? So forgetting has several aspects to it. So forgetting may not be that something doesn't exist. It may just mean that you're not queuing upon it correctly to retrieve what you had in memory. So there are many causes for forgetting itself. So that brings an interesting dimension to all of this. Is forgetting a function by itself? Right? Is it desirable and not just undesirable as we see? Is a question to ask. So, and there are some interesting pointers in neuroscience to that. So there is interesting knowledge that what are called as AMPA receptors lie at the neuron synapse. And when you learn, when neurons continuously adapt, these AMPA receptors can also be removed. So that's equivalent to forgetting on the fly, right? Forgetting as something that's necessary to do rather than something unnecessary to happen, right? And also forgetting is just one part of memory's function. There are papers that suggest that active forgetting helps clear irrelevant information. And forgetting is also known to reduce interference and maintain cognitive flexibility, right? So why am I saying all of this? Is mitigating forgetting the right thing to do in continual learning is something that I'm really trying to bring to the stage here. Let me continue with that point, right? So if you had to just take some quick takeaways from the last couple of slides here as to how the human brain does it. Clearly, treating memory in isolation ignores its role in cognitive control networks, right? So that's been something that's been studied in neuroscience. Memory retrieval is largely goal dependent. You just don't retrieve memory for the sake of it because you have nothing else to do, right? You retrieve, even if you want to remember something, remembering is a goal. You retrieve it for that particular purpose. Okay? It's not just done for the sake of nothing, right? So there's always a goal orientation with memory. And it's also well understood that different brain regions contribute different specialized roles, right? So there is a prefrontal cortex for working memory. There's hippocampus for declarative memory. There's the amygdala. There are multiple aspects of memory. There's sensory motor memory. There's visual memory. There are multiple aspects of memory that come together to help us do our daily tasks. Right? So keeping all of this in mind, the question is now, what's the connection of all of this with continual learning, right? So that's what I want to focus on for the remainder of this talk. So while mitigating forgetting is important, right? So I'm not going to say that mitigating forgetting is not important, but is that the only goal we want to focus on while doing continual learning is perhaps the question that I want to bring. An immediate follow-up of this is, are we paying more attention to what we don't want AI/ML systems to do rather than what they should do? Right? We are saying that they must not mitigate, But is that the way we want to go about building systems, where we inform them on what they should not do rather than what they should do, right? And finally, while forgetting is one axis, should continual learning rather be a substrate to build more adaptive capabilities? Right? So for the remainder of this talk, what I'm going to do is talk about some examples of our own work, right, where we have tried to adapt continual learning to different real-world tasks, and we actually find that you get far more non-trivial problems to work on, a far richer context of problems to work on than just mitigate forgetting. Right? So that's what I'm going to do for the remainder of the talk. Just as a quick highlight of our own timeline in continual learning, we too started with trying to mitigate forgetting many years ago. And our first few papers were all focused on mitigating forgetting. Somewhere around 2022 or so, 3-4 years ago, as we started thinking more deeply about, is that the only thing that you want to do? What if you bring it down with other kinds of tasks? What if you focus more on the adaptation of models rather than mitigation of forgetting? And that's what we've been doing for the last few years, at least. So I'm going to focus on about 3-4 works in the remaining time today, where we've tried taking this to the wild, as I said, on trying to adapt continual learning to different kind of settings and share our own learnings with you, right? So I'm going to probably upfront say that I'm not going to focus too much on the depth of the methods by themselves. All methods they probably borrow different components from existing modules that we all understand, but rather want to talk about the problems that come out of these different settings, right? So, and obviously I'll be happy to discuss towards the end. So one of our first efforts in this direction was a paper in CVP of 22, and the paper was called Unseen Classes at a Later Time. No problem, that was the title of our paper. And what we tried to do here is, how do you learn continually when certain classes in certain tasks could be zero shot, right? We just thought, at that time, our thought was, let's just add some complexity to the problem rather than simply just solve continual learning, at least class incremental learning, the way it was structured at that point in time. So those joint work with students Harichidana, Sumitra, and Shivam. And the first thing you could ask me is, okay, you want to say zero shot meets continual learning. Okay, this was way back in 21. That's when we probably did the work. So a lot of the larger models that you have today was not available in computer vision at that point in time. So it seems to be simple, right? So you probably take some zero-shot method, borrow some idea, put it in continual learning, and it should work, right? So that's what one would expect to do. And that's what we thought too, okay? But as we thought deeper about it, we realized that it was a bit more difficult than just doing that, right? Let me try to ask one of the first questions that you would have here is, how do you design an experimental setting to study this, right? And as we thought deeper about this, we realized there were multiple questions to ask, right? One, do we assume that the unseen classes come only in later tasks and not in the base task? Okay, is that an assumption we have to make? Do we assume that if an unseen class comes at time t+1, it will remain unseen for all future tasks ti greater than t+1? Okay. What if one of them becomes seen in a later task, right? And you can probably see the complexity in this. Right? It's not as linear as a simple class incremental learning benchmark. And that's the main point that I'd like to convey through this is, the moment you talk about continual adaptation over time, it brings in far many more complex challenges than what meets the eye at first sight. Okay, let me elaborate on this. So when we started this work, we took all the related settings and we put that together as this interesting illustration. So you see a bunch of different settings here. You see semi-supervised, you see open set learning, you see zero-shot learning, generalized zero-shot learning, continual learning, class incremental learning, and also open world recognition. So, and you see all of these, what this says in training, what do you see, and in test, what do you see, right? For example, if you take zero-shot learning, you see seen classes in training, and you see unseen classes at testing. And for generalized zero-shot, you see both seen and unseen classes at test time. And in continual learning, we all understand that you have a certain set of classes that you learn at time t. At time t+1, a newer set of classes come, but you also have to test on the older set of classes, so on and so forth, right? So all of these paradigms are well understood to all of you. But as we try to bring in zero-shot and continual learning, we realize that things are not that straightforward again, right? There could be one scenario where You have an unseen set of classes in your base task at the testing time, right? And that remains unseen in all the future tasks. Right? So that could be the simplest thing that you do. You have a bunch of zero-shot classes, and that remains unseen in task time T2, time T3, time T4, so on and so forth. Right? So, and we call that the static continual zero-shot learning. Now, what if things were more dynamic? It could happen that there were a set of classes U1 that was unseen at time T0, and there were a newer set of classes U2 that was unseen at time T1, and an even newer one U3 at time T3, and so on and so forth. Right? Clearly, you can see that even setting up experimental benchmarks for this starts getting complex. Right? In fact, we thought the even more organic setting would be you start with a bunch of unseen classes in your base task. A certain set of them becomes seen in your next task, right? Because who tells you that what you don't see in your first task cannot be seen later? It's possible that at a later point in time, some images come with some labeled images come for that particular class, right? So now that a part of it becomes S2, a part of it remains unseen, and a newer set of unseen classes come. Now, a part of this could get absorbed in S3 as seen classes, and so on and so forth. Now, this becomes really complex. Right? So, as I was trying to say, as you start focusing on adapting continual learning to a wide range of real-world tasks, more complexity starts emerging than just doing the bare-bone mitigation of forgetting. Right? And this is the problem that we try to tackle in this particular work. I'm going to talk about the methodology very briefly. I'd like to focus on the other works a bit more. But as I said, this was an idea way back from 2021. So we used the GAN kind of an approach to do this for generative replay of the samples. This was the overall idea. So we had, I'm sorry. So we had your training samples that come here, which we call as detraining. That goes to a generator discriminator framework where you have your attributes for your zero-shot classes that go to the generator, and the generator generates some features, and the discriminator compares those features with the features that come in from the images and then says which class it belongs to. Okay, this part of the framework is your standard a conditional GAN kind of a framework. And then we use a bunch of losses. We use a cosine similarity based GAN loss, a classification loss, and the loss that really made a difference in this work was this thing called incremental bidirectional loss, where we try to align your class embedding and your attribute embeddings into a common space. Okay, that's what happens with this third loss here. And we also needed a way to do continual learning. We needed to ensure that we store the samples from the past. And for doing that, we were doing generative replay where we use the conditional GAN. Given attributes and some noise, the conditional GAN would generate some features for the classes that you've seen in the past. And at inference, given data from any task so far and given attributes, we had a standard cosine similarity match between the generated features from the data and the attributes, and that would tell us which class a particular sample belonged to. Okay, as I said, I'm going to keep it very brief at this point in time. And using this, we actually showed that be it in any of these settings, right, be it the static setting, dynamic setting, or the online setting, we outperformed many of these methods. And you could see that some of these methods, which were pretty well-known zero-shot methods, don't do well as you start going ahead with continual learning. Right? And this was the table. Once again, we show here that we outperform pretty much all of the baselines here. And here were some qualitative results that we had in this work. Let me just walk over let me walk over this here. This may be easier to see. The unseen class here is the class of a dolphin, and that's the image that comes in at inference. And what we report here in each of these columns is the top 3 cosine similarity matches for this particular image in each task, in task 1, in task 2, in task 3, task 4, and task 5. And you see here that across all of these tasks, our method gets this image to be a dolphin, although dolphin was an unseen class across all the tasks. Right? But what's interesting to see in this result is the other similar classes. Initially was a Dalmatian and a Persian cat, then a Dalmatian and a skunk, a killer whale and a skunk, because till killer whale came in the third task, then it became similar. Then a killer whale and a seal, and a killer whale and a seal in the 5th task. So the similar classes that they had started evolving to newer classes that were coming in over time. As I said, I'm going to talk very briefly about this method, but probably talk a bit more about the takeaways here, right? So if you're interested more about the results or the code here, it's available on archive, and the code is also available. But the takeaways that I wanted to share is that continual adaptation over time in zero-shot settings, while mitigating forgetting is something that you also want to do, but introduces newer complexities that you have to deal with, right? The variations here can actually be combinatorial, right? In terms of how you can spawn off in the variety of settings that you want to deal with. So making benchmarking and studies non-trivial. And it captures real-world challenges more closely than just simple vanilla class incremental learning. This was, as I said, an old work, but let me talk about a slightly more recent work next, which was about continual privacy-aware personalization of human actions with prompt tuning. This was an oral at ECCB last year. And the question that we try to ask here is, let's again take continual learning. But now, what if data in each task was private for some reason, right? What does that entail when you learn continually? It was joint work with students and collaborators from CMU, IIT Hyderabad, and Meta. And you'll understand why Meta, because of this context. The problem here is Meta had this issue of, let's say you build your XR, VR kind of systems, and they had typically pre-shipped with a bunch of gestures that they were trained on, right? So that's what happens for most of these models. Now, the question is, what if the user wanted to add a new gesture because that worked for them better, right? Depending on our geographical backgrounds and cultural backgrounds, maybe I'd want a wave that's different from what I had to do based on a pre-shipped gesture. So this is the question that we were trying to ask. And so the actual way it pans out in terms of the setting itself is you have a set of base action classes, okay, which is what, let's say, Meta trained the model on. And that's in an internal database that cannot be shared, right? So that's obviously proprietary to what Meta built these models on. Now, this particular device has been deployed. It's out at the consumer side now. But the consumer wants to update the gesture recognition system there, or the action recognition system there, with their own gestures. Now, the challenge here is user A may have a certain set of gestures that they want to add over time, and user B may have another set of gestures or actions that they may want to add over time. And we ideally want our model to support both these cases and still not forget the original set of gestures that it had learned in the vanilla model that was shipped. Okay. This translates to some interesting challenges. Okay. So our options at that time was, one is you can train separate models every time a new gesture is added, right? So obviously that's going to spawn off into a wide range of models, but that's a possibility. For each time you have to update your model, maybe the user gives some samples, the model goes back to Meta's servers and it updates the model and loads back a model on the device. Again, not the most conducive solution. But what we ideally went for was, can we ship a model that continually extends to new gestures over time based on the user's personalized requests? Okay, that's what we were trying to do here. That had some interesting challenges to deal with. We obviously want to train a single model that continually extends to new gestures over time. You want the model to adapt to new knowledge. It cannot access older data due to privacy considerations. That's again an issue here. So you just cannot store exemplars and retain them. That's not allowed anymore. And you also have to do this without forgetting the old default gesture classes that were in the shipped model. Okay, that's also a requirement here. So we ideally want to do all of this. Now we realize that this brought in multiple challenges together. One, we want to do continual learning of new human actions. That's a given. There's also a few-shot learning assumption here, because when a user wants to add actions to the model, they're not going to record thousands of hours. They're just going to give few samples because that's the way you want the model to be friendly. So there's a few-shot angle here where the user cannot be expected to provide more than few label samples for the new classes, and your entire model and your learning environment has to be privacy aware. There should be no knowledge of past users' data. It threw in some very interesting challenges. It's still continual learning, but when you bring in these real-world complexities, it brought in very interesting challenges to deal with. Right? So the way we went about it was we used a 3D skeleton sequence as our input because we wanted to be privacy aware. So that way you don't need to worry about storing any images or identity information that can come from your images. 3D skeletons can also reveal identity, but to a significantly lesser extent than images. So the overall framework that we tried to use was we tried to take a feature embedding of your 3D skeletons, and we introduced the idea of adding a prompt offset to your feature embeddings. And there was a reason for that, because we realized that we could not access exemplars from the past, right? So that's something we cannot do here. So what's the next best thing we can do? We realized that a lot of people were doing prompt-based continual learning. We realized that you could still store some random prompts which you can add to your feature representations to represent data coming in from different tasks, right? So every prompt that gets added to your data could probably represent a different task. So you could almost say that these prompt offsets are like your exemplars that are coming in from the past, right? So you'll see this a bit more on the next slide. And once you had, these are additive prompt offsets. And once you have these additive prompt offsets from on the input features, you go to a standard frozen feature extractor and a classifier. Only the classifier is updated based on the newer classes that may come in over time, right? That's the overall idea. But to do this, there were interesting challenges again. So this is the main model that I just spoke about on the previous slide. Now, how do you bring this prompt offsets was the key question that we had to deal with, right? So the rest of the pipeline is something that already exists. You can take 3D skeletons, learn a feature representation, give it to a feature extractor, learn a classifier. That's standard, just standard learning of 3D skeletons. But we had to find a way to bring in these prompt offsets in such a way that they add value for each task. And the way we went about going about this is you have your 3D skeletons, you pass it through a bunch of frozen layers, and then you learn a query embedding layer here. Okay, so this is standard query key value kind of framework. And the query gets compared with a bunch of learnable keys. And you also have a memory of learnable prompts. Right? So wherever you see the fire sign is learnable, you have a memory of learnable prompts. So given the similarity between the query and the key, we actually pick a bunch of samples from the pool memory and add those samples to each of these temporal samples that you get here from the feature embeddings. Why temporal? Because your 3D skeleton can be of action, which means there could be multiple frames. We also learn a sorting layer here, which tells which prompt should go to which time step of this given input skeleton, right? So we also learn that as part of this entire pipeline. Okay. So yeah, and once you have these prompts, you add those prompts to the input features, and the rest of it stays the same as a vanilla standard skeleton classification system. Okay, so to do continual learning, one of the things we realized is that this query function here needs to be updated for new tasks. We also need to update the key parameters here and the prompt pool memory. But the way we go about doing this is to simply just do the cross entropy loss on the new data that you have, the cross entropy loss that comes at the end of the classifier. We just back propagate it all the way through to the prompt pool memory, to the key parameters, as well as this query module, and just use the same loss to get all of these updated. We also introduce a query key clustering loss just to get more compactness in our representations. And with this kind of an approach, we actually had to build our own benchmarks for this, because this, at least at the time of our doing, there was no other paper that was doing something like this for human actions, continual personalization. So we built a benchmark for more activity around actions, which is more coarse-grained, and also hand gesture recognitions, which can be more fine-grained, right? So we built benchmarks for both of these. One of these was built based on a GCN backbone, a graph convolutional network, and one of them was based on a graph transformer backbone. So as you can see, one of the things that we tried to do here is you can use this approach on top of any existing 3D skeleton classification backbone. You could build the prompt offset as something that you can add to it and stay privacy aware in all of this, right? And I hope you saw that there's no exemplar buffer here. The only thing that you have is your prompt pool memory, right? And that's just learnable, so there's no identity information stored in that prompt pool memory. Using this, we actually show that we actually outperform all the baselines, standard continual learning baselines, as well as continual prompt tuning baselines by a significant amount, both in the new classes and the old classes in different settings, right? So we in fact show this. I just have the table here for the activity recognition task, but we have very, very similar numbers even for the hand gesture recognition task. And we also studied the stability plasticity trade-off, and we actually see that our method stays fairly performant across multiple tasks on old classes, new classes, as well as the harmonic mean of the performance across all of these classes. One interesting thing that we observed here is if we compared the, this is the performance of at any point in time, the performance of the model at a given task on the samples from that particular task, right? So once you train your model on, say, task N, how well does it do on task 2, for instance, right? So that's the heat map that you see here. We compared our method, which is called POET, against just a feature extractor. What we mean by a feature extractor is without the prompt offset, just a feature extractor alone. And what's interesting to see is, and we also allowed it to do continual learning here, right? So so sorry, not continual learning. We trained the classifier alone here. In this bottom one, we trained the classifier with the new classes. What we observed interestingly was the feature extraction approach without the prompt offset actually had very, very poor adaptation to new user classes, right? So that was strange to observe. That's what we observed in this particular work. Okay, and this particular application has very, very interesting possibilities, right? So if you want to take it forward, one is while we just did a very simple example of how you a user or two adds gestures over time, you could now think, what if the meta model was actually shipped with a certain set of gestures, but I do that gesture differently because of my cultural background, right? So how do I adapt that at my user end rather than me adapt to the system based on what's pre-shipped is an interesting question. How do you add a new vocabulary of gestures? Can you add an entire new sign language at runtime at the user end? Becomes an interesting question. And there could also be interesting ramifications of inter-user personalization, right? So if I had a family playing together on a particular VR device, then how do I adapt to different users and maybe even share some gestures between them? All become very, very interesting questions, all within the purview of continual learning itself, right? So we still are in the regime of continual learning, but the moment you bring these real-world applications into the mix, the problems become far more richer and interesting to work with. Once again, if you're interested, the paper and the code are publicly available, and you can look at it for more details. So the takeaway is that continual personalization is a pretty challenging problem, especially if you had to bring privacy issues into the mix. While mitigating forgetting is still a challenge there, model adaptation under other constraints makes this more interesting to solve, and it offers a wide range of interesting problems to take on here. I'll try to keep a tab of time. The next work that I wanted to talk about was a more recent work published in AAAI this year, which is continual concept-based learning with vision language models, right? And the question that we try to ask here is, how do you integrate concept-based semantics while you do class incremental learning, right? So you still want to do continual learning again, but now you also want to learn considering concept-based models that could help give you better interpretability, right? So joint work with students, Sushmit, Deepika, and Siddharth. And I'm sure most of you may be aware, but for those of you who are new to concept-based models have been around for a few years now, where you typically learn a feature extractor that gives you a set of interpretable concepts, and your final classifier typically has a linear layer that takes you from concepts to a classifier, right? So today, this regime is becoming more interesting, and of late, there are a lot of NLP works also in this space. And this regime becomes interesting because here is an approach where you can explain your decision intrinsically as part of the learning rather than a post hoc effort that you do after training, right? So that's the idea of concept-based models in general, right? So we've been doing some recent work on how do you not just do concepts in the last layer, but do concepts more distributed across layers, so on and so forth. And I believe that gives a very fundamental way of learning itself, because most neural networks, you know nothing of them between the input and the output. And that's not typically how humans learn at all, right? So we have the notion of intermediate semantics, and concept-based models gives you that notion of intermediate semantics inside a neural network model. But the obvious question that we try to ask here is now, what if you had to do continual learning with concept-based models. To our best of our knowledge, this was maybe the first such effort that was trying to do continual learning with concept-based models. And once again, as we thought a bit more deeply, we realized that this was a pretty complex problem. Why so? As you introduce, this was, let's say, episode 1, episode 2, episode 3, tasks that come over time. As you have newer classes that come over time, things can get complex because concepts could be something that are shared between classes and experiences. A concept that was provided to you at task T1 may be applicable to T2. A concept that came in with a class at T2 may actually be applicable to classify something in T1 much better. And now this starts becoming a very complex web as you learn over time, right? Because it's just not classes that are incremental, even your concepts are now incremental, and the concept class relationships also get incremental over time. So just to explain this better, we actually introduced a new metric called concept class relationship forgetting. And we actually show that if you took a standard concept-based model, a CBM, you realize that it has a significant forgetting factor as you learn over experiences. And we show that when we use our approach, you can learn much better over time using such an approach. Now, so the question here is, how do we learn concept class relationships while learning continually and adapt these relationships? So some of the challenges here were we want to incorporate new concepts and classes in a scalable manner without increasing training parameters. I'll talk about why that is required as we go. We want to integrate concept-based interpretability without doing any explicit annotation. Right? So we don't want to annotate all of your data with concepts again. You just have class annotations, the standard data set that you have, but you still want concept-based annotation. How do you do that was also a challenge. And finally, how do you learn these concept class relationships across experiences while preserving existing ones was another challenge here. And this was our overall setting. I'll get into the framework in a moment, but just to explain the setting itself. So in your episode 1, you have a bunch of images, a bunch of concepts, and a bunch of classes. In your episode 2, you have the same, but now you have a new set of concepts and classes, and your replay buffer that has your concepts and classes from your previous task. And this keeps repeating over time as you to set up this particular setting that we were exploring. For the idea itself, we were looking at working with transformers, which was a little harder because for transformers, even with concept-based models, you typically have a penultimate layer that stands for some semantic concepts that you can reason on and put a linear layer. But for a transformer, you don't have such a thing because at every layer, you're going to get such a set of tokens that are equivalent to the number of tokens that you give as input. So how do you get these kind of concepts in intermediate layers of a transformer was a challenge. So here was our overall architecture. So what you see here was the transformer block. We use a multimodal transformer. We use Flava for our experiments. And our inputs are your input standard tokens. You have your images that go through an image encoder and come up with a bunch of image tokens. Your concept, all your concept attributes that go through a text encoder and give you concept tokens, and your class labels that go through a text encoder and give you the class embeddings. Those are the 3 things that become input to your overall training ecosystem. So one of the first things that we introduce is a concept grounding loss. So where these tokens that correspond to the concepts at the input, you also get the equivalent number of tokens at the end of each block of your transformer. We introduce something called a concept grounding loss that tries to ensure that these embeddings that you get here at the output tokens have a high cosine similarity with the attributes corresponding to the class that this image belongs to, right? So we want these embeddings, these concept embeddings, to be similar to some semantics that we understand. And you don't need to impose this at every transformer block. We just do it empirically at different transformer blocks in different experiments. And we also have something called a concept classifier. I'll come to it in a moment. And our final classification happens through simple cosine similarity so that we stay scalable. So let me walk through each of this in a bit more detail. So our step 1 is to compute your representations that come in as image embeddings, concept embeddings, and your class embeddings. That's standard. And as I said, we have a concept grounding loss where we take these embeddings, send it through a linear layer with a bias, and just ensure that it's dot product with the concept embeddings that we know match well as you learn with different data points. We also have a concept classifier where these concepts that you get here on the previous slide, I'm talking about these set of concepts, those concepts go through a concept classifier to ensure that we can classify concepts that we know exist in that image using those output embedding tokens that we get out of the transformer. This is standard binary cross entropy loss. And finally, a classifier itself is a simple cosine similarity match. We take these concept embeddings that we get for a given input image. We take all the class embeddings that we have of all the classes seen so far, and we build a pairwise matrix, and a row-wise summation tells us how close this set of concepts was to class 1, how close this set of concepts was to class 2 in the second row, and so on and so forth, to get you a softmax kind of an output through which you can get your final prediction. Okay. Now, there are multiple things here, but the interesting part of this is now, where is continual learning in all of this, right? The interesting part is because our final, and in fact, probably this was one of the things that took us the longest time in our entire thinking process to come up with. We realized that expanding your classifier layer, all of that won't work here because it becomes very, very complex to do this when you expand your classifier layers. We realized that just having a simple cosine similarity here meant that you really don't need to worry about continual learning here at all, right? So we do have a replay buffer in this particular work, but other than replay buffer, we need nothing for continual learning because we are anyway going to use a cosine similarity where we take the class embeddings. The only thing that's going to change is the size of this matrix here. As you have more classes, the matrix is going to get bigger. That's all. But otherwise, the rest of the procedure stays the same. Sorry about that. Rest of the procedure stays the same, and you can get your class output by just looking at the softmax output. That's the row sums of this matrix, right? It naturally scales to continual learning when you use a cosine similarity based classifier. Okay. So some key ideas that we had in this work was we had this notion of an extensible concept set that allows us to extend any number of concepts without increase in parameters, because if you just increase the number of concepts that you give at the input, you're just going to get an equivalent number of tokens at the output. That's as simple as that. You don't need to worry about anything else. Using a similarity-based classification was a key design choice for us, and we used a very simple experience replay that stored the concepts and the samples from the past, but we limited that buffer to a small amount, so we only store a small set of samples in this work. Now, where does the interpretability come in this work? So when you learn your concept embeddings that you get out of your transformer, now you run a simple sigmoid classifier on that to find out which of these concepts which concept was most active in each of those embeddings, and that gives you a sense of interpretability while making a prediction. Okay, this interpretability is not post hoc. It's you can tell that this is such and such a class because of the presence of this concept, and this concept, right? And we ran some experiments, and obviously since it was published, you probably know that we got some better numbers than a lot of baselines. But I wanted to just show you a couple of interesting results here. This is a result where we introduce a metric called the active concept ratio, where we try to understand how well do a concept learned at a particular time contribute to the classification in that particular time, right? That's what we try to do here. And when we took a standard concept-based model, we found that only the concepts learned at time t equals 0 were most active for all of the tasks across time. We used a baseline called label-free CBM, which was a little random in terms of which concepts it used for its classification. And when we observed this for our model, we actually saw that it nicely had this diagonal be the most lighted up, because it was using the concepts in each task learned to classify the classes that were introduced in that particular task, right? It was nicely doing that on its own. We were not influencing it in any particular way. And another interesting takeaway from this approach was when we visualized the attention maps of the last layer of the transformer for the intermediate concepts, right? So here is an example. This is a class called a mud turtle. And some of the concepts associated with this class were long, slender neck, small brown shell, and small head. We found that the attention very nicely visualizes on the long, slender neck here, on the small brown shell here, and the small head here, right? When you compare it with a bare-bone transformer, you actually see that the attention heads are all over the place. Okay? And what is interesting here is we never trained the model for this. This is an emergent property. just by introducing the notion of concepts while learning continually, not only was it trying to predict the concepts and then learn the classifier, it was also localizing the concepts to understand which part of the image it was the concept was located in while making the prediction, okay, which made this result pretty interesting by itself. Okay, once again, if you're interested, you can look at this for more results and analysis. But the takeaway again is that this was another example that continual learning, when you integrate it with tasks like concept-based learning, face far more unique challenges. The classifier being parameter-free was a key design choice that actually took us quite some time to decide in this particular work. Right? Once again, offers a lot of other interesting problems to solve. I'm sure many of you can think of ways of extending this going forward too. Right? And the last piece of work, this was very, very recently done, it's under review at this point, was we tried to see now, how do you learn continually when classes in your later tasks could come from long tail distributions, right? So which means it's not as balanced, and you could have a long tail in some of the classes that come in later tasks. Okay. This is under review at this point in time. So once again, I think you could probably think this is continual meets long tail learning. How difficult can it be, right? So you probably know where I'm going with this. But the first question is, can't we just take long tail learning strategies and just add them to CL methods? That's the first question one could ask. We also thought that's what we could do until we found something very interesting. Right? We found something called the transitioning heads conundrum, right? And what we observed was, because of maintaining your exemplar buffer that you store between tasks, we found that what was a head class, right? Long tail continual learning is typically divided into two subset of classes: head classes which have a lot of samples, and the tail classes which have just a very few samples, right? Standard long tail learning. What we found was, the moment you start storing samples in your exemplar buffer, the head classes in task T1 start becoming tail classes in T2 because you stored very few examples. That the number of samples was actually equivalent to the tail classes of your task 2, and so on and so forth. Right? Once again, this gets pretty complex. And interestingly, what we actually found was that over tasks, the samples that dominated in our data set was actually what we call as these transitioning head classes. So each time you have a set of samples that belong to a head class, but in the next task that becomes a tail, which we call as a transitioning head. And then that keeps accumulating as you keep doing continual learning. And over time, what really becomes of the highest amount in your data set is your transitioning heads data. And what we also saw was, if you take a state of the art, so in fact, we took a method that worked in the space of long tail continual learning, and we actually found that it performed pretty poorly on the transitioning head. In fact, that's the set of samples that it performed the worst on. It actually did well on tail reasonably, and also the other head classes reasonably, but the transitioning heads is where it got its significant hit from. And we actually showed that using our approach, we are actually able to address this transitioning head problem. So how do we go about doing this? Very, very quick preview to this. We realized that most of the existing methods don't separately treat your head classes and your tail classes. So we decided that in our approach, we must have a head expert and a tail expert, because otherwise we really cannot address this problem effectively. So we had a head expert and a tail expert in the problem, but that was not it. So here was our training strategy itself. So we start with a standard imbalanced data loader. That's your long tail kind of a data loader. And we provide it to your head branch and a tail branch. So you're learning two different classifiers here. And that's what you see as the output embeddings. This is the classifier head. This is the classifier tail. And we also introduce a loss that tries to, for the head branch and the tail branch, that respects the sampling complexity in each of these. But the other important part that we needed here was, we also then had a step where we tried to do what we call early knowledge transfer from the head class to the tail class. We realized that when you do continual learning and you go from task 1 to task 2, your head class is likely to become a tail class in the next iteration, in your next episode. And hence, we do a knowledge transfer, a knowledge distillation between the head class layers here and the tail class layers here. So we take the exemplar replay buffer samples and provide it to the tail class, and try to see if its softmax outputs match the logits, rather. The logits here match the logits of this when it was passed to the head class. And we do this before doing continual learning. And that's why we call it early knowledge transfer. And we found that this was very, very key. So to some extent, what we're trying to tell the network is, hey, this particular head class is likely to become a tail class in the next iteration. Let the tail expert be ready for this in the next step. Okay? That's what we try to do here with this early knowledge transfer. And with this approach, we actually get pretty strong results against a host of baselines from continual learning and long tail. So once again, here the experimental settings become pretty complex. We test ourselves on something called ordered long tail recognition as well as shuffled. In ordered, you assume that the tail classes are only introduced in the non-base classes in a very structured manner. And in the shuffled approach, the tail classes can come randomly in any task, right? Your first task, your base task could have head and tail. Your next task may not have a tail class at all. Your task 2 later could have a bunch of head classes and tail classes, and that's the more organic setting that we really wanted to address. And that's what we call as a shuffled long tail continual learning setup. So here are some qualitative results to show that our model actually maintains the identity of that sample across multiple class. This was one of the transitioning head classes that we studied here. And we actually saw that the state of the art, which was actually a paper which came, I think, CVPR last year, which was a long tail continual recognition method, actually started performing pretty poorly on these kinds of transitioning head classes. I know I'm close to my time. I'm going to conclude in a minute or two. So just to circle back and conclude with the thoughts again is, now what does all of this mean, right? So obviously I was trying to say that maybe forgetting is not the main thing to look at. So let me try to circle all of that back and put things in perspective. So obviously memory is a key scaffolding for intelligence, and it may be important to recognize that forgetting may be a feature, right? So often we measure forgetting accuracy with continual learning. Maybe forgetting something is useful, right? How do you tell that apart from just checking forgetting on all samples that you have is a fundamental question to answer, right? So we don't have an answer at this point in time. While memory as an entity has operations, it's driven a lot by its function. Right? I think this is an important line. What I think I'm trying to say is, while we store exemplar buffers and we learn continually using different methods, what perhaps would make it more powerful is how you actually adapt it to real-world problems. Right? So that's what I was trying to go with when I said in the beginning that continual learning being a substrate for solving a wide variety of problems is perhaps a richer approach than just mitigating forgetting in very, very simple benchmarks. So this may mean that maybe we should revisit our goals for learning continually, a means to adapt rather than just forgetting being an end by itself. And an interesting takeaway from all of these samples that I gave is that continual learning seems to have a multiplier effect once you take it to a diverse set of problems, right? So zero-shot learning by itself was not hard, but the moment you made it continual, the time dimension actually starts making it hard, right? The continual personalization example that I talked about, if you just had one user gesture to add, maybe simple, but the moment you have to add multiple user gestures over time, the continual part of it over time actually makes it hard. Same with continual long-tail recognition that we just saw a couple of slides ago, right? So continual learning actually has a multiplier effect. It has an exponential effect on any task that it's applied to just because of the time dimension that we bring in, right? So how do we bring in more organic benchmarks and settings to study this in more real-world tasks is something that I really wanted to vouch for. And just as a concluding slide, maybe something to think for, I don't have a clear answer, I'm going to leave it open-ended, is the title of my talk was Beyond Forgetting. And the question here is, beyond forgetting, what should it be, right? Maybe this is a venue to discuss that. It's something for the continual learning community, rather ours to define at this point in time. My pitch would be, some of the possibilities would be, look at adaptation more than forgetting. And adaptation would have different metrics and different ways to measure in different problems. Integration with multiple real-world tasks could be the more organic way to study the performance of continual learning. Personalization, reasoning, or even imagining new things the way human memory does. With that, I'll stop. Thank you again for having me here. Would like to thank all the students, alumni, collaborators, colleagues, and funding bodies that have enabled all these efforts that you saw. And happy to take a few questions if we stop here. Go ahead.
Hi, thank you for your very interesting talk. I had a couple of questions about the concept-based work. So in that work, were you treating concepts as mutually exclusive, or were you training with like a multi-label loss?
What did you mean by mutually exclusive? There could be multiple concepts that define a particular class.
Right, okay. So how did you define the task stream based on these concepts? Were you building it in a hierarchical way such that concepts were building on top of each other over time, or did you study other policies?
That's a good question. That's an ongoing work of ours.
Okay.
But in this, we were relying on standard concept-based models where you typically just have a set of concepts that defines a class, right? So there are no abstractions within concepts. But I think that's a very interesting question. That's what I meant by saying that once you bring that in, there's more complexity to deal with. But in this particular work, we just assume that they're a flat structure that defines the class. And in terms of test sampling itself, maybe I can talk offline into the details, but having the cosine similarity classifier took away any other complexity because we just take all the concepts that came in through a particular input image, compare it with the class embeddings that we have for all the classes so far, and wherever we get the highest summation of the similarities is what we classify. It's a very simple classifier.
Okay, thank you very much.
Thank you for the wonderful talk. Despite you citing my paper as being one of the ones that had all that forgetting stuff, we put it on archive in 2017, even though it came out on that journal in like 2019. I absolutely agree with you. And I blame, I don't know, like the initial papers like set stuff up, and I feel like it then locked in some people's thinking and they just keep doing the same thing. I don't do it anymore. I even write papers railing against it now, saying that doesn't, that's basically solved. Let's work on more interesting things, but those papers don't get cited. The the earlier ones do. Anyways, so two things that I've been thinking about. So I think these are great kind of problems and application spaces, but two, like just to align them more with conventional sort of things I've been focusing on. Computational efficiency and forward transfer, right? The idea that past learning should make future learning more efficient, and also how do we use continual learning to kind of like minimize the amount of time that we spend learning. So I kind of wanted to get your take on that beyond more like, I think it's great doing, like showing continual learning can have impact in the real world.
Got it. I haven't thought about that much myself, but my hunch towards that is, I think I probably alluded to that in the beginning. I didn't revisit that, but that's something that we've been working on. I don't have any results to show at this point, is to make memory far more than just a buffer, right? So that's, we believe that memory has been significantly underused in continual learning, just keeping it as a buffer for a large part. I think adding more versatility there, adding more layering there, which is perhaps what humans do, is something that at least we've been betting on to actually make that more nuanced. Yeah, I'd love to chat with you later too.
Yeah, and forgetting is something I think, we need to forget. We forget all the time. It's useful, but kind of like our metrics, we kind of ignore that. Thank you.
Hello. Hi. Andrea Santoggio. Okay, it's working. All right. Sorry for that. Loughborough University, UK. I really like how you started your motivations, right? And this idea of using memory from a functional viewpoint, and as you say, support a lot by neuroscience research as well. And what's interesting for me is that, and this is part of the question was already mentioned in the previous question, is that I work in lifelong reinforcement learning, and I personally couldn't care less about forgetting because all we care about is how the memory is functional to new tasks. And so, as was mentioned earlier, forward transfer, backward transfer, sample efficiency are metrics that have been developed in lifelong reinforcement learning for a very long time. And I was always wondering, like, are people using these metrics in classification? I think they could be used, and it would be really, really interesting. And some of the things you were showing, like reuse of features, and eventually, I think what is really cool is that lifelong learning is about empowering the acquisition of more complex tasks. And so essentially is how much can I leverage what I've learned in the past for what I'm learning, right? And I saw a lot of very interesting things. I wonder if you have considered using some of these metrics or some of like these viewpoints borrowing from reinforcement learning. Thank you.
I haven't worked on RL much, at least in the continual setting, so I don't have a very nuanced answer to it, and I'd love to chat a bit more offline, perhaps. But I think more maybe I'll give a broader answer, mainly because my answer would be no otherwise. I haven't thought about that aspect directly. Is maybe a point that I'm not sure if I left it subtle, but a point that I wanted to convey when I talked about memory as a function in the beginning is, while these just seem like different use cases in practice, right? So these seem like different applications. That's the point I was driving at, that memory as a function essentially is driven by how you use it, right? And memory can take different shapes and forms based on how you use it, which is why I think I was trying to convey that continual learning as a substrate to doing different applications may actually be far more powerful than just focus on just continual learning and not forgetting. That's the point that I think I was trying to convey across this. So in that sense, yes, but I haven't specifically thought about methods from RL, how it can be brought in here. I'd love to talk a bit more to understand your perspective.
I think we
Thank
are
you.
running late, so we will stop here, but you can ask more questions to Vineeth during the break. So let's thank Vineeth once again.